Alright, so far we've looked at uniform circular motion, which is circular motion where the speed of the particle moving along the circular path does not change. And we've looked at quantities such as the position vector, the velocity vector, which is v equal to r omega theta hat, and the acceleration, which is a centripetal acceleration. Let's look at a couple more important quantities. First, we have the time period t, which is the time taken to traverse or complete this circular path once. Now, because we have uniform circular motion, where the speed of this particle moving along this circular path is constant, this time period t is a well-defined quantity. The time taken to travel this circular path once does not change. Of course, if the particle is slowing down or speeding up, then this quantity is not so useful anymore. So this time period t is really useful for uniform circular motion. Okay, can we express this t in terms of omega, the angular speed, the constant angular speed, right? So the length of this path is of course a circumference, it's 2 pi r. Then the time period t is 2 pi r divided by the constant speed, which is v. But v is equal to r omega, so that t equal to 2 pi by omega. That's a useful formula. Let's look at another quantity, which is the frequency. The frequency is the number of times the circular path is covered per unit time. So what are the SI units? So of course, this is the number of revolutions that's covered per unit time. So in SI units, you would have revolutions per second. Revolutions is just a number, so the unit is basically per second, right? And another way of saying that is that, and another popular name for that is hertz, okay? So let's try to relate frequency with time period. So if time period is measured in seconds, right, then in t seconds, by definition of time period, you have one oscillation, because time period is the amount of time required to cover one oscillation. Then just by unitary method, you know that every second there are 1 by t oscillations, but frequency is by definition the number of oscillations per second. So f equal to 1 by t equal to, because t was 2 pi by omega, f is omega by 2 pi. We can now use some of these quantities. We can look at them in the context of a simple problem. Alright, here's the statement of a problem. I've picked this problem from the Resnick-Halliday-Walker book called Fundamentals of Physics. That's the book that we recommended for this course and from which we picked some suggested problems for you to solve. So you can pause this video at this point and try to work your way through the problem. We're going to look at this in detail right now. Okay, so from the statement of this problem, we understand that we have a fan. Let's simplify that design. You have a fan. You have, like, let's say you have 3 blades of a fan. We only need to think of 1 blade, right? And what this fan is doing is that it's, of course, the blade has a length of what, 0.15 meters by the statement of the question, and the fan is rotating at some constant angular speed, right? Some constant angular speed. What's the speed? What we've been given is that the rotating fan completes 1200 oscillations every minute. So what is that? What we have here is a statement about the revolutions completed in some unit of time. So this 1200 is actually a frequency, right? Okay, so let's list that down. We have f equal to 1200 revs per minute. If you would like to complete this problem in SI units, then you might want to convert this into revolutions per second. Let's do that actually. So that's just 1200 per 60, because 60 seconds in a minute, right? and then you have 20 revs per second. Okay, that seems like a reasonable speed for a fan. So in question A, they asked us through what distance does a tip of the fan move in one revolution. Well, that's just a geometry problem, right? It moves a distance of, well, equal to one circumference. So for part A, the answer is just, let's call it S, the distance traveled by this tip in one complete revolution. That's just 2 pi times 0.15 meters, whatever that is. Alright, that was an easy one. Next, in B, you've been asked to find the speed of this tip. Well, how far away is this tip from the center of the fan? It's 0.15 meters. The whole fan, not just this tip, this whole fan is moving with some angular velocity. In which case, what would the speed of this tip be? It would be v equal to r omega, right? Where r would be 0.15 meters. Alright, but what's omega? We do have f though, right? But we know that f equal to omega by 2 pi. So that omega is just 2 pi f. We can substitute that then, which is 0.2 pi times 0.15 times 20 meter per second. That's the speed of this tip here, right? This tip moving, this direction. Okay, all well and good. What about the next one? What's C? You have to find the magnitude of the acceleration of this tip. But this acceleration, as you know, is given by v square by r or r omega square, whichever you feel comfortable with. Of course, we have omega equal to 2 pi f, and we do have f, so probably that's the quickest way to get about it. So that this is just this is just r times 2 pi f squared, but then that's just 0.15 times 2 pi into 20 square, and then the units are meter per second square. Alright, so in part D, you've been asked to find the period of motion, but as you know, the period is just 1 by f, which is 1 by 20, and that will be in seconds. Alright, so in part E, we want to find the velocity and acceleration of a point that's halfway along the blade, which is, a distance of 0.075 meters along the blade. So the velocity will be given by v equal to r omega again. Notice that the whole fan, not just the tip there that we were talking about a minute ago, but the whole fan is traveling with this angular velocity. So the linear speed of this point here would be just v equal to r omega, and then that's just 0.075 times, well, omega would be 2 pi into 20. So that's interesting. Notice that, of course, in meter per second. Now notice that this speed is exactly half of the speed of the tip. Why is that? There's an easy way to think about this. It's that this whole fan, not just this tip, this whole fan has to complete a revolution, a whole revolution in the time period t, right? But in that time, this tip has traveled this whole circumference, right? While the point in the middle at this same time has to travel only half the distance. So it's natural that the linear speed of this point here, halfway along the blade, is exactly half of the linear speed of the tip of the blade, even though the angular speed of this whole system, of this whole fan, is omega. Alright, and similarly, if you want to consider acceleration, you would have to evaluate using this formula, r omega square, and again you get that 0.075 times 2 pi times 20 square meter per second square. Again, that acceleration is exactly half of the acceleration of the tip. So this is all well and good. We leave you now with a summary and some important formulae in uniform circular motion. Some of these formulas will come in useful when doing problems. Sometimes the quantities given in the problem may not correspond exactly to these two formulas, so you'll have to rearrange on your own and try your best to solve problems as efficiently as possible. Thank you.